Good morning, everyone. How many people in here are Java developers? Just by a quick show of hands. Okay, let me rephrase that. Who is not a Java developer in here? Okay, why are you here? I'm just kidding. I'm just kidding. The joke gets worse from here, so you've been warned. Let's get started. There's a break after this, right, Katie?
Yeah.
And I can use the whole break to do the rest of my presentation, right? Okay. Katie says that's what I should do, so that's what I'm going to do. Okay, why not, right? It's a 30-minute break, though, right? Just okay. I'll probably run into the break since we're getting started a bit late here. But if you have any questions while I'm going through this, please feel free to ask them at any point in time. Happy to take a pause and talk about whatever the current topic is. As Katie said, my name is Pratik Patel. I'm a Java champion based out of Atlanta. You may have read one of the books I've written. I work at a company called Azul Systems. We only do Java virtual machines. So for all the Java devs in here and non-Java devs, you probably know what a JVM is. We actually have a high-performance VM called Zulu that gets 150 million downloads, actually more now. It's completely free. It's our build of OpenJDK and our contribution to the community. And we also have a high-performance JVM called Platform Prime, which again is for high performance. And I'll talk a little bit about that during this presentation. But this is not a product pitch. This is talking about cloud cost optimization specifically for Java workloads. And we also have a really amazing next generation product called Code Inventory and Vulnerability Detection, which is runtime detection of vulnerabilities. And the code inventory part lets you know what code you're actually executing in production, which is amazing because if you're like every other software company or software shop, a software team, you know that there's a lot of code that you don't actually run. But wouldn't it be amazing if you could find out what that code was and just get rid of it because you know you're not actually running it in production, right? So I can talk about those out in the hallway after the presentation if you're interested. And one of the things about our high-performance VM is that it is a drop-in replacement for OpenJDK or Oracle or whatever, and it gives you an instant performance boost just by swapping out the JDK. So for example, one of our customers, I can't tell you who they are, but they're the world's largest retailer and they end in Mart. You may have heard of them before. They're one of our customers. They dropped it in for Apache Kafka and saw huge gains on it. Okay, so enough of that. Let's start off with some questions. How many people are on the cloud or deploying stuff on the cloud today? Okay, so I expected less people here because, you know, the kind of things that happen in this area. Which cloud provider are you guys using out of curiosity? AWS, okay. You raised your hand also, right? Azure, okay. Anybody else? Anyone using GCP out of curiosity? Okay, one GCP person. Now I will say that even though this presentation is focused around cloud cost optimization, if you're running on-prem, you can still get the same benefits because as all of you know, servers and infrastructure and a data center and all that kind of stuff is not cheap. There's a lot of operational and capital costs that go into it. So it doesn't really matter which cloud platform that you're using. What matters is how you use it and, you know, using it to the max. And the other side of that coin, of course, is using less of it to save money, even if you're running in your own data center, right? It gives you more headroom and stuff like that. So the next question is, what's the best way to reduce cloud cost? It's not a trick question. I have trick questions later. So anyone want to take a quick guess? Okay. So of course the answer is turn off your servers. This is a very small podium, sorry about that. But the real answer is it depends on your application because every application, as you know, is different. It'll have a different performance and usage profile, and we'll talk a little bit about that during this session to give you an idea of what you can do to kind of make your application use the compute and memory power that you have underneath it to its maximum efficiency. Okay? And the other answer is that there is no one-size-fits-all solution. When I work with the Azul customers and we look at how they're running their applications, whether it's on the cloud or in on-prem or whatever it may be, their app, how it runs, what kind of performance characteristics it has, makes a big difference. And of course, what it's doing, bursty traffic and other things like that. But before we jump into that, I want to talk about cloud pricing for a few minutes. Okay? So here's a question for you. Does the cost of cloud compute go up, down, or stay the same? And let's time box this and let's say over the last 5 years. Okay? So by a show of hands, how many people think the the cost of cloud compute. Now, specifically just compute, right? You can also throw memory in there, but I'm not talking about like services and API gateways and stuff like that. Sorry. How many people think it's gone up over the last 5 years? Okay, reasonable guess. How many people think it's gone down over the last 5 years? Okay, nobody, one person. How many people think it's stayed the same over the last 5 years? Nobody, okay. So the answer to this question is in this graph, right? Now, I found this graph. There's a reference to it. We'll share the slides at some point. Katie, can you give me some water, please? You can see that if you look closely at this graph, right? Again, this is approximately over the last 5 years. You see it starts in 2019 and it goes to about last year sometime. So let's say over the last 5 years, okay? Now, there's this interesting inflection point right here where it says the period during which AWS and Azure launched lower priced Graviton and Epic-based VMs, okay? Now, you can see that there's a significant drop. I would say that this is probably somewhere between 7 and 10% drop in the cost of compute. And of course, this is, thank you. This is taken from, or these specifically is for US East, which is, as most of you would know, outside of DC, and it's specifically for AWS. But as you can see here, aside from this specific situation with Graviton and Epic-based VMs, the prices basically stayed the same. So the answer is it's actually stayed the same, right? Now you might be thinking, if you are somebody who's been doing this for a while, you know that Moore's Law doesn't really apply anymore, but there is still efficiency in new generation chipsets and CPUs, right? So you would expect this to continue to go down. But what's actually happened is that because the cost of everything has gone up over the last few years, electricity, manpower, right? People to staff your data center and all that kind of stuff, the cost has actually stayed flat instead of going down. If you were to look at this more historically, let's say we went back 10 years, you would see that the cost of compute has actually gone down over time, okay? But because of various different things, increased cost essentially, and maybe a little bit of profit taking, but I don't know the ins and outs of how AWS or Azure, or for that matter GCP, price their things and what their actual operational costs are and things like that. It stayed the same. Okay. Now, how many people are familiar with what Graviton and Epic-based CPUs are? A few people know. Okay. So Graviton is basically ARM64-based CPUs. Okay, and Epic are AMD-based x86 CPU architectures. Okay. Now, the reason why Graviton had such a big effect here is because Graviton doesn't have amazing single-core performance or single-threaded performance, but what it is, it's very wide and it's more energy efficient, and of course the CPUs cost less, but the main part is that it's more energy efficient. So if you look at the pricing, and we'll get into this in a little bit in terms of exact amounts, you can take your Java application, and unless you're doing native calls, i.e. using JNI, your app will just work. Whether you're running a Spring Boot application, or you're using some other framework, or you're just writing straight Java. We've had customers move from x86-based, i.e. Intel architectures, to Graviton, and they see an immediate 20% improvement in cost. Now, the performance per core is a little bit slower, but what can you do in that case? You just add more cores, and you still save money, okay? So this is an immediate win if you're looking for a way to go and impress your boss or your team and say, hey, I can bring down our $100,000 a month compute bill, EC2, elastic build, whatever, just by switching to Graviton. Of course, you want to try it out first, make sure your app will run. But again, if you're not running JNI, then it's pretty easy to just go switch over to Graviton and just save a huge bunch of money right out of the gate, okay? But we'll talk a little bit more about that in a few minutes, okay? But when we think of the pricing factors, it's always not just compute. But I'm going to focus on compute in this session, specifically compute and memory. I don't want to talk too much about storage and network and APIs and shared services and databases and stuff like that. Because if I start talking about that in terms of the overall picture for cloud cost and how to bring it down, we would be here for about 3 to 5 hours to talk about all those things. Okay, so we want to keep this short and sweet, focus on compute and memory, right? But I do want to talk a little bit about architecture before we jump into some more of the specifics around the Java virtual machine, right? So this is a diagram I came up with a while back. It basically talks about what are the different overall kind of large, broad brush architectures, right? Everyone knows what a monolith is. In a monolith-based architecture, you basically are doing vertical scaling. Vertical scaling means that you get more you get more horsepower for your application by adding more CPU and memory. It's extremely difficult to do because what you have to do is you have to physically get a machine that has more cores or a machine that has more memory. Of course, nowadays you can go and go to your cloud console, or if you're using VMware or whatever, select something that has more of both, but you have to bring your app down and then you have to bring it up with more of that, right? That's vertical scaling. And that is basically not elastic because it's not on-demand scaling up or down, okay? And then of course, somewhere in the middle you have microservices. And microservices also have the capability of doing what's called horizontal scaling, and it is very elastic. So if you're running in Kubernetes, for example, you can say that I want to have a cluster of 10 nodes, and I'm going to run my app in it, and I'm going to scale that down or scale it up beyond 10 nodes if I need to, and you can do that very easily by a simple configuration, and sometimes even automatically if you're using auto scaling. And of course, cloud functions or functions as a service are the ultimate in horizontal scaling because it automatically scales up and down for you. It handles a whole bunch of stuff, and it's very elastic, okay? So the reason for talking about this is because elastic style compute helps you get cost control, especially if you're using auto scaling. The system detects that you don't have as many operations coming in or as many requests coming into your application, so it will shrink from 10 to 7 or 5 or however many servers are actually needed to service that load and still have good user response time. Okay, so I'm still not a huge fan of Kubernetes because it's very complex and it requires a lot of overhead, in my opinion, to be able to manage properly a kube cluster, but you get the idea here. Okay. So the other kinds of architectures around this, of course, is platform as a service. You may remember Heroku, or you may have used that in the past. And I kind of lump containers as a service, CaaS, and Kubernetes into the same bucket. I think of CaaS as Kubernetes without any real management overhead, right? You basically go and give a CaaS platform. If you're not familiar with the offerings from the cloud providers, this would be something like Amazon Fargate, AWS Fargate, Azure Containers, and Google Cloud Run. So you say, here's a Docker container, go run this stuff for me. And it will go and run this stuff, and it will scale up the number of simultaneous images of your Docker container, and it will go run that. And I don't want to spend any time on cloud functions because we don't have a lot of time to talk about that in here. Okay. Now, I do want to take a quick aside here and point this out. So this person is a researcher at Google, and that's one of the important bits here at Google. And they came out with this fascinating study, and you can read the whole thing at some other point, but basically they said that our prototype implementation of using a modular monolith versus a microservice reduced application latency by up to 15x and reduced cost by up to 9x compared to using microservices, right? So how many people write or deploy microservices in here, out of curiosity? Okay, so a few people, okay? So now, when we think about this, well, why did we move to microservices, right? And why are microservices so inefficient? You could probably guess what the answer here is. When you build a microservices, you're running small services, and there's a lot of communication that goes on between microservices, and you have to do JSON serialization and deserialization. That adds a huge amount of overhead and compute power required to do that. You also have to send stuff over the network. That adds latency and also adds overhead, right? Compute overhead. Okay, more network overhead for that example. But what I would suggest you do is go have a look at this, and it actually makes for really nice reading to understand, like, if you're building a system, what are the trade-offs that you're making when you go from a monolith to a microservice. I'm not saying you should stay on a monolith, but you probably have heard people talk about modular monoliths, and there's a great presentation from Spring I/O of May of this year where someone from the Spring team talks about using Spring Framework to build modular monoliths. So you can read this paper, you have a look at what they mean in a deep dive session on modular monoliths, and why it can help reduce overall cost and, of course, latency. Okay, so let's dive into the Java part for a few minutes and talk about some JVM considerations. All right. Surprisingly, and I know it's not cool, well, everyone in this room thinks it's cool because you're Java developers, but if you talk to non-Java devs, they're like, oh yeah, Java's like, it's kind of past history, it's not cool anymore, it requires too many letters to, to build software. Anyways, Java is actually a great language for the cloud too. It's extremely power and cost efficient. It's very flexible. You can build almost any type of app for it. And again, the JVM has been around for almost 30 years. So it's 30 years of improvements to the Java virtual machine in terms of performance and lots of other things. And it can be a language for all different types of application models. Okay. Now, one of the other things that makes the JVM really nice in terms of power efficiency is that we have something called a just-in-time compiler. If you're not familiar with what that is basically there's a bit of software inside the JVM, and what it does is it looks at your code and it makes it more efficient as it gets executed. It does advanced things, for example, like call-side caching. A common one is method inlining. So whenever you call a method from another method, which calls another method, what happens is every time a method is called, you put something on the stack. And then when that method is run, you pop down the stack, right? But that adds overhead. So one of the low-level optimizations that can happen here is if the method is called over and over and the JIT sees that the same result is always returned from that method, it just takes that method and inlines it in that branch of code so that you don't have to hop on the stack and hop off the stack, right? So it saves a little bit, but when you execute something millions of times in a minute or 10 seconds or whatever, all these things add up, right? That's just one of the optimizations. There are hundreds of optimizations in the VM. It's one of the reasons why Java applications actually get more efficient over time because the JIT is continuously optimizing your code and making it better. Okay? Now, you do have a little bit of warm-up time that you have to accommodate for as the JIT kicks in and analyzes your code and makes it faster. Okay? So, in terms of power efficiency, this is, well, unfortunately you can't read it because of the font color, but you can pull this up. Some folks at a research lab wrote the same application across a bunch of different languages, and they opened up a server and attached multimeters to it to measure watt consumption and other things like that. But you can see they actually measured in joules. Of course, if you did EE, you know that you can convert watts to joules. Joules basically means how much power you're using here. Okay? Now, again, this is the same application. They ran it for several hours and took measurements out of all these different programming platforms. And you can see Java is the most efficient. And for those of you who might be running C#, you can see it comes in at a close second. So yes, indeed, some empirical evidence in terms of how much, basically how much power a application uses using Java versus others, right? And the reason why this is important is because something that's power efficient essentially means that something is CPU efficient. Because what draws the most amount of power in a server or a computer? It's the CPU. Obviously, the memory also requires power, but it's the CPU that usually, like, if you're playing a video game or doing some kind of video transformation, you'll hear your CPU spin up the CPU fan spin up because it's drawing additional power, okay? And just for giggles, I put in some of the interpreted language, and, we were talking about how people love things like JavaScript and Perl and other things like that, Ruby, for example. But you could see that if we go back one, Java uses approximately, let's call that about 40 joules for this specific test. And something like JavaScript, this is hard to read, but I looked at this up on the table. This draws about 100 or something like that. So it's about 2.5 times less power efficient than Java, okay? And again, I did not come up with this. You can go look at the link and you can have a read through this article, okay? But again, the point about bringing this up is to talk about power efficiency and CPU utilization go hand in hand, all right? So let's talk about some specific JVM optimizations, and let's look at some runtime JVM specifics here to give you an idea of how you need to think about how do I right size the number of CPU cores and other things that I have in my application? Of course, that has stopped for some reason because it fell off the table. So what I'm going to do is I'm going to draw a quick diagram that shows, not of me, of this, that shows how the JVM starts up and what the CPU utilization is over the lifetime of a JVM app, or let's say at least the early lifetime, okay? So I'm going to put two axes on here. Uh-oh, why does this not work? I did test all this today, so, okay, there we go. Okay, so on the bottom axis, I'm going to do time, and on the vertical axis, I'm going to do CPU utilization, okay? So what happens when the JVM starts up? It loads all the classes. If you're using something like Spring Framework, it goes and constructs all the metadata that the Spring Framework uses, i.e. your Spring Beans. It makes database connections, sets up objects for the thing to start running. So initially when you start up, you start using a lot of CPU because it's loading those classes, doing all that initialization of the framework, of your code, and all that kind of stuff, right? So at some point, what happens is we hit something called app ready, okay? So that means that the app is ready to service the first request, okay? So at this point, everything is loaded, first requests start coming in, we start taking requests, and our CPU utilization goes up, and then eventually the JIT starts kicking in, and we reach some level of JIT efficiency, where we start really going down in terms of CPU utilization, and then as the JIT optimizes more and more code, let's say we hit this point, we're at about 98%, and I kind of made this number up, but this is, let's just go with it, right? 98% code efficiency. So this delta right here is basically where the JIT is doing optimizations, okay? Now, when we size a server to run our application, what do we typically do, right? We're developers. So we will go and use the latest library, which is fresh out of the Git oven, and throw it into our application and say, let's go, let's use this new shiny thing. But when it comes to operational things, we're much, much, much more conservative, right? Because we don't want our pager or our phone or whatever blowing up on Saturday night or late on Monday or whatever. We just want this thing to run because we don't want to make ourselves and our team look bad. So what do? We over-provision the amount of compute and memory we have in our application to avoid the app crashing basically because of overutilization, right? So what we do in this case is we will say, okay, right, again, the vertical axis is CPU. So what we'll do is we'll add some extra threads or cores or whatever, and we will set our baseline to be like up here, right? So this is the amount of CPU allocated, and I apologize for my terrible handwriting. That's the amount of CPU we allocate, but if you look at this application, you could see that we kind of peak like right about here, right? So we peak right about here in terms of how much CPU we're maxing out. But we want this headroom right here in case we get bursty traffic, right? Right, so we know that the JIT is optimizing our code and we're getting more efficient, i.e. we're using less CPU over time. So we actually have two problems here that we need to solve if we want to get the maximum amount of efficiency, i.e. have the lowest cost for running our actual application, okay? So the first is the obvious part, which is this right here, okay? How can we avoid over-provisioning too much? Because this is all waste, right? We're basically wasting our money here because we've over-provisioned the number of cores, threads, virtual cores that we've assigned to this. Now, in all fairness, AWS, at least I know, has a feature that you can enable which says, I want a dynamic number of cores for this EC2 instance for this amount of time. So you can actually go into the AWS console and say, for the first 10 minutes, allocate an extra 2 cores to this, because I know I have this curve where I'm going to be using more compute power as the app gets set up and as the JIT kicks in and has not yet fully optimized my code, okay? So you can do that, and that is helpful, but wouldn't it be nice if we didn't have to worry about that kind of low-level stuff, okay? Now, the other part that's wasted is this part right here, right? This is basically our JIT warm-up time. If you remember, I had this on a slide earlier, warm-up time. Again, I apologize for my terrible handwriting, but you get the idea, JIT warm-up time. So this is also wasted CPU cycles. Now, with the AWS Dynamic Core modeling, you can avoid that by just assigning a few cores and you can get over that hump. But what about the over-provision part, right? That's what we're trying to solve here. Because this is over the lifetime of the application that we're worried about that, right? We basically want our baseline to be somewhere around this neighborhood, right? Yes, you'll see ups and downs, so you will need to over-provision a little bit to capture when you get heavy traffic. Because as you know, every application doesn't have traffic that's just flat like this in 24 hours of the day, right? If you're building something in the fintech world, when the markets open up at 9:30 in the morning, you get a surge of traffic and then it kind of levels off, and then at lunch it goes down, might come back up, whatever, right? It's kind of up and down. Think of whatever your application is, right? If you're doing if you work for a retailer and you're doing like a sale, you get a lot of traffic at certain parts during the day or certain parts of the week where you have people trying to buy stuff off your website, right? You think of your application and it's usually traffic is up and down like that, okay? So there are a couple of things here that we could do to alleviate the over-provisioning. First thing is to bring that ceiling of over-provisioning down a little bit and basically take a little bit more risk. Say, all right, I'm going to bring that down and not have as big of a safety net and I'll save some money. The other way is to just have a more efficient JVM. And this is one of the things that Azul Prime is good at, is we have a much more aggressive JIT compiler, so it can actually bring the threshold for how much basically CPU it uses down, because our JIT, which is called Falcon, it is a proprietary JIT, it will optimize your code more aggressively so that your app will actually run more efficient over time. And on top of that, Azul Prime, our high-performance VM, also has hundreds of optimizations that make things faster compared to OpenJDK, okay? So, and of course, we also have our own garbage collector, which is a continuous garbage collector, which helps also with high-performance JVMs to have a high-performance JVM. Okay, so I know I'm just a bit over time, so I'll start wrapping this up with some quick additional tips here. We've talked a little bit about this. I don't want to go into GC pauses right now because that's actually a much longer discussion about what you can do for a garbage collection. That's an entire presentation to itself. Right, so one thing that we might be considering is, well, if your JIT takes a long time to warm up, does that mean short-lived processes, for example, if you're running in a cloud function or running in a microservice in Kubernetes, where maybe your app is only up, or sorry, specific instance of your app is only up for 10 minutes or 20 minutes, and the JIT takes a while to warm up, right? So let me ask you a question for the Java devs in here. Say you have a medium-sized Spring Boot application, 20,000 lines of code, okay? And you exercise this application across most of the code paths, i.e. you put it under heavy load. So for an application of that size, how long do you think the OpenJDK JIT, the just-in-time optimizer, takes to reach, let's say, 90% efficiency? Anyone want to take a guess? How long do you think it would take? For a standard Spring Boot application, right? Let's say it's a RESTful or serving, some JSON endpoints or something, or maybe even websites. How long do you think it takes for that thing to reach peak efficiency, near peak efficiency, 90%? You want to guess in the back there with the hat?
No.
Chandra, you want to take a guess? 50 seconds for a 20,000 line Spring Boot application. Okay, that's a guess. Anybody else? 90. Okay, it's not a bad guess. You're getting closer. So for an application like that, it typically will take 10 to 20 minutes for it to reach peak efficiency. Again, about 80, 90%. The other assumption is that we're putting it under moderate to heavy load so the JIT can look at all the code paths and stuff like that. So the JIT does take a little bit of time to get warmed up, okay? Again, we made a lot of assumptions there. Standard modern Spring Boot application, running it on modern VM, and under moderate to heavy load. Okay, so it does take time to reach that level. Of course, we reach a lot of the things which are quote unquote low-hanging fruit in terms of the JIT compiler. will get optimized much faster. So, the curve doesn't look like flat down like this. The curve looks like this and then tails off as I drew previously, right? You have that long tail where it gets harder and harder for the JIT to actually optimize code because it's optimized all the things which are easy. Now it's looking at more advanced things to do to optimize, okay? Anyways, now one way to alleviate this is that JIT optimization warm-up time, right? If we go back to this chart, wouldn't it be nice if instead of having a curve where we have, there we go. Instead of having a curve that goes up like this, wouldn't it be nice if the curve just looked kind of like this, right? That would be great because now we don't have to worry about this extra waste here, which will always be there because that's how much we provisioned our application for. So Azul also has another proprietary product called Ready Now, which will be able to provide a JVM, a warmed up JIT that you go and warm up in like staging or somewhere in your test environment. Or we also have a very advanced product called Cloud Native Compiler, which is a server that sits in the background and it can push JIT optimizations to the 10 or 100 servers running that specific application over the network. So you only have one server using CPU to optimize your code, and you push stuff to all the instances of it so you get this flat curve, well, more flat curve that I just showed. Okay? All right. So we talked about these things already, talked about Ready Now and Cloud Native Compiler. I don't want to get into garbage collection because that's a bit of a longer discussion, like an hour or longer. JIT gets more efficient over time, which we already configured. Okay, and I've already talked about this stuff, Ready Now and CNC. So let me just close out very quickly on stuff that you can do. We talked about not over provisioning as much to save cloud costs. Right, so just make that extra headroom you have less. One of the actual biggest factors in cloud cost waste is actually quite simple. It's the second bullet on here. It's essentially VMs that you're running that you're not using. So you're working on something. Okay, I'm going to try this out. You go and run it. You spin some stuff up on AWS or in your data center or whatever. And you're like, oh, it's noon, it's lunchtime. I'm going to go get lunch. And you just leave it running. Or you just go home for the night. You're like, oh, I'll pick this up tomorrow, right? So it's actually something really simple that can actually adds up over time. And then there's kind of similar to that is the lack of automation around cloud cost, right? If you're able to automate more stuff and be able to like bring servers up and down when you need them, instead of just leaving them up running all the time or just more longer than they need to. If you had automation around that, that can also significantly reduce cloud costs. Okay. Now, these are kind of more non-technical things here, but a lack of governance, right? If you don't have a team within your large organization which sets rules for how you're supposed to use cloud services and what you shouldn't use and what are like some guidelines or even rules around what you're allowed to spin up and things like that. Lack of governance leads to cloud cost, and of course lack of guardrails, right? You throw something out, something spins out of control, and now all of a sudden you have like a $10,000 a day bill because someone left their performance test running on production for like a week instead of shutting it down, right? So having guardrails around that where you don't just keep scaling up and up and up automatically and your cloud cost goes through the roof, okay? The last one you're probably familiar with a little bit, which is unexpected egress and ingress charges. This basically means data transfers into and out of your cloud platform are not cheap, sometimes not even cheap within the same cloud provider between regions. So there are some ways to ameliorate that, but not really a lot. So, okay, we talked about this stuff already, dealing with non-uniform load. Nobody has load that's consistent. I like CaaS over Kubernetes for simplicity because you can get that auto scaling. You say, here's a Docker container with my application. Just go run it. And it goes and runs it. Of course, as you know, nothing in life is free. Running a CaaS solution like AWS Fargate, Azure Containers, or Google Cloud Run is more expensive than just spinning up your own VM, EC2 or whatever, right? So they add a little bit of cost to it. So you have to figure out for yourself if it's worth running a CaaS versus managing your own Kube cluster or how are you plan to deploy it, okay? So, all right, and we haven't talked much about cloud functions, but cloud functions are the ultimate in elasticity because they aggressively scale up and scale down. You don't have to do anything, it just does it for you. But it does require a new way of architecting your applications because cloud functions generally should be very, very small. And to give you an idea of what very, very small means, it should be no more than 100 or 200 lines of code total. Again, 100 to 200 lines of code in a single cloud function. And you might be asking, well, if that's the case, how do I write an application? Well, cloud functions are meant to be small units that do one thing, so you write loads of different cloud functions and you weave them together to build a full application, okay? But that's an entirely different topic. Again, I have a great presentation on serverless for Java where I talk about this if you're interested in seeing that for your team or for your company, okay? And I mentioned Graviton early, so I want to close on this. A couple of key stats here. Graviton is typically 50% less expensive than x86 for compute, right? The trade-off here is that Graviton doesn't have great single core, single vCore performance, but again, it's all about scaling horizontally, wide, as opposed to scaling vertically, right? So you can add more cores and still save money. And Azul also has a build for ARM64 for a high-performance JVM. So if you go to Graviton, boom, you're saving 30, 40, 50% right off the gate. And if you use Prime with it, you can actually save an extra 25% in compute power because, again, our high-performance VM is 26% faster than OpenJDK on Graviton. And that's because of all the low-level ARM64 improvements we've made in our code. Okay? All right, so one last thing I want to talk about very quickly is some of you may be running or looking at managed services instead of doing DIY. Now, what do I mean by this? Okay, say that I want to run Cassandra or I want to run Kafka. Kafka's still hot, right? Anyone building stuff with Kafka here today? No? Okay. But you're familiar with what Kafka is, right? Some folks in the back there. So you might say, okay, I'm just going to go to AWS or GCP or whatever, and I don't want to manage a Kafka cluster, so I'm going to use their managed Kafka service. Okay? Now, starting on managed services, in my opinion, is always a great idea because as you're building an application, a new application especially, or you're adding Kafka to an existing application, again, I'm just using Kafka as an example. This could be any managed service. It's great to be able to just focus on building your application rather than worrying about all this infrastructure stuff, right? Because you have deadlines and deliverables and stuff like that. So starting off with managed services when you're not using a lot of it is actually a great idea. But at some point what happens is, if you were to draw this in a chart, if you look at cost and you look at your utilization, at some point the charts diverge like this, where your cost is not matching the amount that you're using previously because you're using much less of it. So the question in terms of cloud cost is, can I save money by using a managed Kafka, again, or a managed service of some kind, versus is it cheaper for me to manage my own Kafka cluster, okay? And the answer to that question is that you have to kind of model out when I hit 1 million Kafka messages an hour, when I hit 10 million an hour, where's that line for me? Because obviously, when you manage your own Kafka cluster, now you need to have a Kafka specialist or two within your team or your company. How much does it cost to employ that person versus how much am I paying AWS to have managed Kafka, right? So again, you'd have to draw a graph and where that inflection point is, where it costs more to use managed Kafka versus the flat line of including personnel costs for managing your own Kafka cluster, right? So basically, when is doing it yourself worth the money and the time? Okay. All right. So with that, I know I'm over time, so I will shut up now. I'll take a couple of questions since we still have a break. But if you wish to see the more extended version of this presentation or one of the several other ones I have on cloud architecture and Java, please hit me up. My email address is pretty easy. It's just ppatel@azul.com, or you can find me on Twitterverse, at PR Patel, and on Blue Sky, and on LinkedIn as PR Patel. Okay, so thank you for coming. I hope you enjoyed that.